Hi guys, welcome back to the channel. In this lecture we are going to discuss about the plastic collapse mechanism in simply supported beam, right? So this is a very important lecture, right? So till now in plastic analysis we have discussed about what is plastic analysis, how we can take the advantage of plastic analysis in our design, okay? And basically we studied that this method is applicable to steel structures, and in some cases we can apply this for RCC structures also, right? So now let us come to this topic, right? So till now we have discussed about the advantages of plastic analysis, what shape factors, those things, okay? Now this is a very important lecture. Many things will get clear from this lecture, okay? So basically before starting this lecture, we have some this curvature, moment curvature diagram, okay? The actual diagram was like this, okay? Up to here we will be having the elastic behavior, okay? This is the elastoplastic and this is the plastic behavior, okay? So now for our simplification we have idealized this curve like this. Okay, now this up to here we will be having elastic state, and here this is plastic state. So what we did in this idealization is that we neglected this elastoplastic behavior, okay? Whenever a section is changing from elastic to plastic state, we will be having some elastoplastic behavior, okay, in that section. So that part we are neglecting, okay? What we are assuming is that up to this point the beam will behave elastic, okay? And when it just reaches to the collapse moment, it will become plastic, okay? So the transition, this elastoplastic transition, we have neglected to simplify our calculations, okay? And corresponding to this we will be having some load displacement curve, and it will look like this. Again, actual diagram will be like this, okay? Again we will idealize this diagram. So up to here this is our elastic, and this is plastic, right? So this is basically we idealized this is basically the elastic plastic analysis, right? Where we are having the elastic state and then we are having the plastic state, right? So this method is also called elastic plastic method. Now let us come to this topic, right? So let us first draw the simply supported beam, okay? Its length is L, okay? So now when you are applying this load W at the center, and due to this W load, let us suppose the deflection at this point will look like this. So this is A, this is B, right? And here let us suppose we are in this stage, okay? In this stage, this is our W load, okay? And this is our, let us suppose, delta deflection, right? So this is our, here this is delta deflection, okay? Now when I increase this W load to let us suppose Wy, increase this W load to Wy, okay? So now if you look in this let us suppose the cross section of this beam is rectangular cross section, okay? So corresponding to this W, initially the stress diagram will look like this, and here the sigma is less than sigma y, yield stress, okay? Now if you increase W to Wy, this yield load, then the cross section, then the stress diagram at this cross section will look like this. This is sigma y, this is sigma y. So this is corresponding to the yield load, and in this displacement curve it will be here. So this is our yield load, okay, and corresponding to this yield load we will be having some deflection yield. You can say that this is, let us suppose, rho y, okay. So when we increased this w to wy, the deflection diagram will look like this. So let us suppose this is del y, okay. So now this is okay. Now if I increase this w to wy to wc, means we are just reaching the collapse condition, okay, and this is our wc, right? So what happened when we increase our load to wc? So when we increase this load to wc, the deflection diagram there will look like this, okay. There will be at this section we will be having some hinge formation, okay, and this is nothing but this is plastic hinge, okay. And we know that this rho y, this del y will be equals to wy L cube over में 48 EI, okay. In this I am considering this fully elastic. The cross section I am taking fully elastic, okay. Now when I increase my wy to wc, the deflection at this collapse, which is this deflection del c, is equals to wc into L cube over में 48 EI, okay. Again I am assuming that full section is elastic, okay. This is we are getting through this idealization basically, okay. Up to here this is pure elastic behavior, right? But in actual this is not this is not the case, okay. At this cross section we will be having in this, actually we neglected this elastoplastic behavior basically, right? So what we did with this assumption is that we have just increased the stiffness value, okay. We have increased the stiffness, right? Actually while considering this I will be this what you can say that this is our actual curve, okay, and we have assumed and this idealization, okay. So you can see that this is the to get this deflection, let us suppose this deflection we need to apply some load P, okay, P1, and to get if we are using this actual curve, okay, and if we want and this is, let us suppose del 1, right, and if we are using this idealized curve for the same del 1, we need to increase our load, okay. This is P2, so P2 is greater than P1. So basically while taking this assumption, this idealized curve, we are making our structure more stiff, okay, but that is not the case. So now let us come to the topic. Del C is basically WC into L cube over 48 EI, okay. And here I am assuming, one thing I am assuming is that the portion between these two hinges, this is the simply supported beam, and let us suppose this at this point there is the plastic hinge form at the center, right? So this portion is elastic, this portion is completely elastic, right? And only here we will be having some plastic. This is the plastic portion at this point, right? So we are also neglecting while in our discussion we are also neglecting the effect of the effect of the plastic hinge length, okay. So we are neglecting the effect of plastic hinge length, okay, plastic hinge length, right? Because if you see this cross section, let us suppose if this is a cross section, this is the side, this is the, if I'm seeing this beam at this from this side, so actually there will be the plastic hinge will form like this. Okay, but we are assuming that the plastic hinge only forming along this cross section only. We are neglecting this hinge part. This length of this, the plastic hinge length we are neglecting. Okay. So this portion is basically elastic. This portion will be elastic. Okay. So now one more thing. During the yielding state, this curve, let us suppose this is curve 1. Okay. And during the plastic state, during the, what you can say that this is the, you can say that this is the 1. Okay. And this is, let us suppose this is, okay, this is curve 2, right? So now what is happening is that, and when this plastic hinge is formed, now see carefully, when this plastic hinge is formed, this beam will deflect, this beam will be having deflection, with constant load. Okay. So now when the beam reach this collapse mechanism, just starting point of the collapse, again for the plastic collapse to happening, for mechanism to form, this will deflect like this. Okay. So this portion, this deflection basically is happening due to constant load. Okay. After that we will, when we increase this load to WC, there will be constant deflection. Okay. Why this deflection we will see now, right? And this is, let us suppose this is curve 3, right? So curve 1, curve 2 and curve 3 will be same. Curve 2 and curve 3 will be same. Okay. Because the moment capacity is not increasing. Up this section is already reached to MP state. Okay. So it has some deflection curve. Okay. These are basically bending deformation. Beyond that, it cannot provide any resistance to bending. Okay. So these two curves will be same, right? But due to constant load, but when the plastic hinge is formed, after the formation of the plastic hinge, it will deflect with constant load. Okay, that you can see here. When it reaches the MP, there is a deflection, there is increase in curvature at constant MP, right? Here also you can see that there is increase in displacement at constant load WC. Okay. So now what is happening when we reached the at the start of the collapse, you can see that at the start of the collapse, this is look like this. Okay, and when the hinge, then plastic hinge is formed, we will be having some mechanism. Okay, so this is basically due to, this deflection is due to basically plastic rotation of hinge, rotation of plastic hinge, right? And these two curves are same, that we have already discussed. Okay, so if we just think about the plastic collapse, so when this load is WC over here, and we are, and our fibers and the cross section at this location reached to this point, this is sigma y, this is sigma y. Okay, when this thing happened, then there is a formation of the plastic hinge at this point. Okay, and the plastic collapse mechanism will look like this. Okay, so don't get confused over here. I have drawn the displacement diagram for this portion only, between these two states. from when the collapse displacement already happened, and after that it moved with constant load. Okay, so so this deflection, let us suppose this is delta 1, so this is equals to delta 1. Okay, and the variation between these two will depict this thing. Okay, but you can say that this will be, let us suppose, del 1, so this will be del 1. Okay, this was our deflection at the start of the collapse. Okay, and beyond the collapse I have drawn this displacement, what you can say that this I have shown this displacement of this beam, okay, due to collapse mechanism, right? And what is the meaning of mechanism? Basically, when the plastic hinge is formed over here, it cannot provide, its bending stiffness is basically 0, its EI is 0. So when EI is 0, it can have indefinite amount of rotation. Okay, when the bending stiffness is 0. So at this point the bending stiffness is 0, so it can have very large amount of rotation. Okay, so when the rotation is more, then this delta 1 also will be more, right? And because this delta 1 is due to rotation of this plastic hinge. Okay, but if the rotations are infinite, very very large rotation, then the shape, then the geometry of this beam can change. Okay, and the equilibrium condition will disturb. Okay, so now equilibrium condition, if let us suppose, what I meant by that is that if this is the beam, and if you are saying that it will be having the infinite rotation, and let us suppose it becomes like this. Okay, so here what you can see here, what will happen is that this load W will be balanced by, some part of this W load will be balanced by this bending, and some part will be balanced by this axial forces in these two parts, right? But this thing we are not considering in this plastic analysis. Okay, so we are not saying, we won't say that it will rotate through indefinite amount of rotation will be there. Okay, so at some point there will be the collapse of beam will take place. Okay, and this is basically this delta 1. Up to here we will be having delta C, and this is delta 1. Okay, so total deflection up to the collapse will be nothing but delta C plus delta 1. Okay, so now this delta 1 is happening under the constant load. Okay, so there will be some rotation. This is theta, this is theta. Okay, here will be some theta. Okay, this movement is basically under the constant load. Okay, and actual movement will be this. Right? So now what is now there is one more thing which I would like to discuss, is that this is the total deflection. This is the what you can say that this delta 1. So if I want to calculate the delta 1, I can calculate like this. Delta 1 is equals to, this is L by 2. So it is equals to nothing but L by 2 into theta. So this delta 1 is basically L by 2 into theta. Okay, we can use the trigonometric concept to calculate this delta 1 deflection, right? So one more thing. So what is mechanism? Basically mechanism is nothing but, now when we reach this WC load, okay, when we increase this W load to WC, there is formation of the plastic hinge. Okay, and slight increase of load, or if you give a little deflection at this point, it will deform without any resistance, without generating any resistance. So mechanism is nothing but, it is the combination of hinges which will make structure displacement without any rotation, structure displays without any resistance. Okay, there is no resistance to this movement. Okay, when the load is increased to WC, then there is no, after that there is no resistance to this movement. Okay, because it can rotate about indefinite amount. Okay, it can rotate about indefinite amount. The bending stiffness at this point is 0, and we are assuming that this load is balanced only by bending, not by axial forces. Okay, remember that thing. So this is the mechanism condition. Here this single hinge, after the formation of this hinges, this structure is turned into mechanism, which means that there will be some displacement in the structure, but without any resistance, without generating any resistance. Okay, there won't be any resistance to those displacement. Okay, so that is basically the mechanism condition. That structure is under mechanism. Okay, so this is basically the plastic hinge. So, and this is basically the basic idea how the beam collapse under this beam collapse. There is how the beam plastic collapse take place in the simply supported beam. Okay, and one more thing is that the point between these two curves, we are assuming that these are elastic, but actually it is not the case. Okay, up to there we have already discussed this thing. There will be some plastic hinges, elastoplastic behavior. Okay, in actual there is some elastic plasto behavior for some distance just left and just right to this hinge point. Okay, but in our discussion, in our analysis, we have assumed that we are neglecting this elastoplastic behavior. Okay, and this length of this plastic hinge and this length of the plastic hinge and what you can say that along this member is important thing. Okay, if you want to have a detailed analysis, or you can say that if you want to have a accurate analysis, then you need to consider this variation also, elastoplastic behavior also across the cross section and along this member. Okay, because elastoplastic behavior we are neglecting across the cross section, means we are in this cross section also there will be some elastic plastic behavior that we are neglecting, and along this member also we are neglecting. Okay, so if you want to have those accurate results, then we need to consider those things also. Okay, so guys, this is the basically the part of the what you can say that the plastic collapse of this plastic collapse of this simply supported beam. Okay, one more thing we will discuss over here. Okay, so when this load has reached the Wy value, Wc collapse value, just starting of collapse. Okay, so at that point the moment will be Wc equals to, the moment at this section is Wc into L/4, and this is nothing but this will be equals to mp movement. Okay, and this is through statics. Okay, so this Wc into L/4 we already know. For simply supported beam, the maximum moment will be at center, and that value will be Wc into L/4. Okay, these two parts will remain elastic. Okay, and the Wc value will be 4 into mp over L. Okay, this is basically a we use the concept of statics over here. Okay, we calculated the moment and we equated it equal to the plastic moment, right? And there is another one, kinematic approach to calculate this Wc. Okay, so in that what will happen is that these two curves are very important. Okay, why we have assumed this assumptions, we can get through this curve, right? So now if this is the mechanism condition, okay, after the application of Wc, this beam will deflect under the constant load, right? This is theta, this is theta, here also this is theta, this is theta. This is simply supported, so there won't be any moment will be 0 over here, moment will be 0 over here. Okay, And this part we will be having some MP, and here also there will be some MP moment. Okay. Now let us now we will use in the kinematic approach, we will be using the concept of virtual work done. Virtual work done. In virtual work done, in virtual work done, what happens is that total external work done, total external virtual work plus total internal virtual work is equals to 0. Okay. So now what is the virtual work over here? Total external virtual work. When this load is increased to WC, now if you give the slight displacement of this amount, this delta amount, okay, this deflection is not due to this load basically. Okay, this is basically due to the plastic rotation of these hinges, right? Or you can say that due to this WC load, when this is deflected by delta amount, okay, under this constant load, okay, so this deflection is not due to this WC load, right? So the external work done will be WC into L by 2 into theta. This is delta, and we have already calculated this is L by 2 into theta. Okay. So we are giving this displacement delta, okay, after reaching this collapse load. So the total external virtual work will be WC into L by 2 into theta. That deflection is not due to this WC load. That's why we are calling it as virtual work. Okay. Plus internal virtual work will be MP into theta. Sorry, this is minus MP into theta. This is minus MP into theta. And this will be equals to 0. And what will be the internal virtual work? At this point, at this location, at this hinge location, this is the plastic moment basically. This is the plastic moment of resistance, which will be opposite to this rotation basically, which will be always be opposite to this rotation. Rotation here is clockwise and this moment is basically anti-clockwise. That's why there is a negative sign. Minus MP into 2 theta. Minus MP into theta. Similarly here the rotation is what is the rotation? Rotation is anti-clockwise, and the moment generating at this point is clockwise. So this is minus MP into theta, right? This moment will always opposite to this theta value. Remember that thing. Okay. So now this will be WC into L by 2 into theta. This is 2 MP into theta. Theta will cancel out each other. So WC is equals to 4 MP by L, right? So this is through the kinematical approach. Okay. In the books, they will do that in some books they will do that total external work will be equal to total internal work. Okay. So what they will in the books they will write total external virtual work will be total internal virtual work, right? So the external work is nothing but WC into L by 2 into theta, and this is equals to the more internal work which will be absorbed by these hinges. Okay, so this is nothing but MP into theta plus MP into theta. This is equal, this is both are the same things. Okay, both actual thing will be this, right? So what they did over here is that they just simply equated these two external work and virtual work. Okay, so here you can use the concept of virtual work done method, right, to calculate the deflection. And what is the virtual? Because here we are using this virtual displacement. What is the virtual displacement? This basically this delta 2. This delta is we are applying. Let us suppose we are giving that as a virtual displacement. Okay, we are giving that displacement as a virtual displacement. Okay, this delta will act as a virtual displacement for this load because this displacement is not due to this WC load. That's why we have used this term total external virtual work. Okay, and this internal resistance is not generated due to this rotation. This has already there. This has been already there. Okay, so remember that thing. So I'm treating this delta as a basically the virtual displacement. Okay. So guys, if you have any doubt in this lecture, you can write in the comment section, because this is a very, very good concept to learn what are the assumptions we are making in our simplified analysis. Okay. So if you have any doubt, you can write in the comment section, right? So thank you very much. We'll meet in the next lecture.